it will transfer the content of next memory location into the H register. Next memory location means 3556. So, in this way LHLD used to work. The purpose is to load HL pair directly from the memory location content into the HL pair. The second one is the SHLD. The SHLD is the store HL pair content directly. LHLD is used to copy the content from the memory to the HL pair, and SHLD will be used for storing the content of HL pair into the memory. So, it works similarly, but the purpose is little bit different. One is copying from the memory to the HL pair, and SHLD will be copying from the HL pair to the memory. So, the syntax of SHLD is SHLD 16-bit address. Of course, it is again a 3-byte instruction, where the second and third byte represents the memory location where the content of HL pair will be stored. So, what it will do? It will transfer the content of L register to the specified memory location. If 3555 is the memory location, so first what it will do? It will first copy the content of L register into that specified location, and then the H register content will be copied into the next memory location, that is 3556. So, purpose is same. LHLD and the way LHLD used to work and SHLD used to work is same, but the source and the destinations are different in case of LHLD and SHLD. Now, the third instruction is XCHG, exchange, and what it does? It exchanges the content of HL pair with the D pair. This is a single byte instruction, and the syntax of using this instruction is XCHG, simple. XCHG is simple. So, this is 1 byte instruction, no address is provided, and its purpose is to exchange the content of HL pair with the D pair. When it is being exchanged, what does it mean? Whatever is the content of H will become the content of D, and whatever is the content of D will become the content of H. Similarly, whatever is the content of L will become the content of E, and whatever is the content of E will become the content of L. So, this is 1 byte instruction, and the content of H register are exchanged with the D register, and the content of L register is exchanged with the content of E register. Now, it is not possible to exchange the content of H with E or L with D. Whenever the exchange will take place, higher order register to higher order register and lower order register to lower order register. The second, the next category of advanced instruction is related with the arithmetic group. Previously, whatever I have discussed, these 3 instruction, it is related with the data transfer instruction. Now, with the arithmetic group. And arithmetic group, there is a instruction that is addition with carry. Now, the addition with carry means carry bit also included while doing the any addition. So, if it is ADCR, now the syntax of ADC instruction is ADCR or ADCM or ADI 8-bit, and the purpose is to add the content of the operand, the carry bit and the accumulator. What we have studied till now, add R, ADDR. What it does? It adds the content of R register with the accumulator, and the result will be stored in accumulator. What ADCR will do? It will add the content of register, it may be any register, with the content of accumulator along with the carry bit. Carry bit also will be added, and it will store the result in the accumulator, and due to this flags are going to be affected. Similarly, ADCM will work in the same fashion. It will add the content of memory along with the carry bit to the accumulator, and the result will be stored in accumulator. What ADI 8-bit will do? It will also add the content 8-bit along with the carry bit with the accumulator, and the result will be stored in the accumulator. Similarly, it will be doing subtraction with carry. Till now, subtraction instruction we have studied SUBR. What it does? It subtracts the content of register from the accumulator and the result is stored in the accumulator. Now what this will do? It will subtract the content of register from the accumulator along with the borrow or the carry bit of from the accumulator. So two things are going to be subtracted. One is the carry bit, the carry value, that is 1, as well as the content of the register R. These are subtracted from accumulator and the result will be stored in the accumulator. Similarly, SBBM works. Similarly, SBI 8-bit works. Now the very important instruction is double register addition. Now till now we have added a 8-bit register with an 8-bit number. We have seen the addition of 8-bit number with an 8-bit number. Now, but there is a provision by an instruction called DAD by which we can add a register pair with another register pair. And the syntax of using DAD instruction is DAD RP. Now what is this DAD RP? It adds the register pair to the HL pair. Which register pair? It may be BC pair, it may be DE pair, it may be HL pair, it may be stack pointer. Of course, this is also a single byte instruction because no 8-bit or 16-bit data is being provided along with the instruction. So what this will do? If it is written DAD-B, what it will do? It will add the content of BC pair with the content of HL pair and the result will be stored in the HL pair. If it is written DAD-D, it will add the content of DE pair with the content of HL pair and the result will be stored in HL pair. If we have written DAD-H, it will add the content of HL pair with the content of HL pair and the result will be stored in HL pair. If it is written DAD-SP, it means it will add the content of stack pointer with the content of HL pair and the result will be stored in the HL pair. And of course, the carry flag is going to be affected. It will reflect the result of the 16-bit addition and no other flags are going to be affected. The next instruction is the instruction which is related with the program counter and the stack pointer, and the instruction which comes under this category is XTHL. XTHL stands for exchange the top of the stack with the HL pair. Whatever is the stack top content, जो stack हम use कर रहे हैं, memory के portion को stack की तरह use कर रहे हैं, उसमें जो top 2 content होगा वो exchange हो जाएगा किसके साथ? HL pair के साथ. This is single byte instruction and the content of L register are exchanged with the content of memory location shown by the stack pointer and the content of H are exchanged with the content of memory location of SP plus 1 in the next. So before using this instruction, the stack pointer must be initialized previously, then only it can work. So what it will do? It will exchange, and whenever I say exchange, it means the content of memory will be coming into the H register and the content of H register will be going to the memory. So you have to be very clear about XTHL. And the content of L register will be exchanged with the, so similarly it works. Now some more instructions which are related with the program counter and the stack pointer. The first one is SPHL. SPHL means it is going to copy the content of H and L register into the stack pointer. If we want that stack pointer to be loaded by a 16-bit number and that 16-bit address is already present in the HL register, then we can use the instruction SPHL. It will store the content of HL register into the stack pointer. Of course, it is also a single byte instruction. The content of H register specifies the higher byte and the L register specifies the lower byte. And the content of HL pair are not going to be affected because you already know that in case of any data transfer instruction, source is not modified, only destination is going to be modified. So whenever we copy the H and L register content into the stack pointer, whatever is the previous value of a stack pointer, that will be replaced by the content of H and L register. Similarly, we have another instruction PCHL, and it is going to copy the content of HL pair into the program counter. This is also a single byte instruction. The H register content specifies the higher order byte and L register is a lower order byte. So whatever is the content of HL pair, it will be copied in the PC. So you already know that HL pair, whenever we talk about HL pair register, it is a 16-bit register. Whenever we talk about SP, it is also a 16-bit register. So, what it is going to do, it is copying a 16-bit number from the HL pair register to the stack pointer, and PCHL is going to copy the content of HL pair register, which is a 16-bit, into the program counter, which is also a 16-bit register. The next instruction in this category is the CMC. CMC stands for complement the carry flag. Now, till now we are not able to change the condition of the flag until unless we are not doing any arithmetic on the logical instruction, but this is the instruction by which we can make the complement of the carry flag. This is single byte instruction. If the carry flag, previous value of carry flag is 1, it will become 0. If it is 0, it will become 1. And the last instruction in this category is STC, set the carry flag. Without doing any arithmetic on the logic operation, just by using STC instruction, whatever is the content of carry flag, it is going to be set after its execution. If it is 0, it will become 1. If it is 1 previously, it will remain 1. So, that is all about the different advanced instructions used in 8085. Thank you.